Hey, Dr. Brown, this is Brooks, and I'm just going to show you how I derived my formula for finding a polynomial of any data set of points in 2D that, of course, aren't vertically stacked. And I derived this on my own when I was attempting to solve the problem that you mentioned in discrete math that we never actually did for homework. It was the problem that was that we had to derive a polynomial that passed when given integer inputs, it outputs as many consecutive consecutive primes as possible. So I started with a small example where, oh my goodness, well, I didn't start with that, I'll tell you that. Let's see if I can select this puppy. All right, let's get a new section in here. All right, that's good. So I started with a simple example where I thought I needed a polynomial that when given 1, it outputs 2, the first prime, and when given 2, it outputs the next prime, and so forth, just like you explained in class. So I started with 4 primes, let's see, with those primes. And just to give my polynomial that spits out primes a name, I'm going to call it paragraph of x, big P of x. And I was thinking, you know, it's really hard to make a polynomial that passes through more than one point. I mean, I could make, excuse me, more than 2 points. You could easily make a polynomial that passes through 1 point, you know, just a parabola and shift it around. You could make one that passes through 2 points. You could make another parabola, make it hit one of the points, and then just squeeze it and shift it around till it hits the other one. That's no problem. But through 3 points, I don't know, that's kind of hard. Through more than that, I was just toast. But then I realized something. I realized that, you know, if I add up 2 functions, what I'm really doing is I'm just adding their y values when evaluated at that x. So I figured, couldn't I have my big P of x equal to the sum of 4 different polynomials? Okay, the sum of 4 different polynomials, which itself would be a polynomial, right? But with the caveat that this first polynomial here would pass through this point, the first point, but would have zeros at x equals 2, at x equals 3, and x equals 4. If it has zeros, then its values there are 0. The second polynomial, this guy, he's going to pass through 2, 3, this guy, but he's going to have zeros at 1, 3, and 4. And so on. The third polynomial here, this guy, he's going to pass through 3, 5. But he's going to have zeros at 4, 2, and 1. And so on for the last guy. The last polynomial will pass through the point 4, 7, but will have zeros at 1, 2, and 3. So that's how I figured out, you know, maybe I could just design a polynomial, a simple polynomial, as simple as I can get it. Excuse me, that's my phone going off right there. All right, nobody I know. Nobody calls me from Missouri. All right, so this is what I was getting at. Four polynomials that pass through 1 point and have zeros everywhere else. It's really easy to give a polynomial 0. So here's how I'm going to define my function that passes through these 4 coordinate points. It's going to be f sub 1 of x plus f sub 2 of x plus f sub 3 of x plus f sub 4 of x. Now f sub 1, like I said, is going to need to pass through the point 1, 2, and have zeros everywhere else. So let me get a different color out so we can figure out f sub 1 of x right here. It's really easy to give a polynomial zeros. So let's give it zeros at x equals 2, at x equals 3, and x equals 4. All right. It's not finished yet, but that's certainly a part of it. Now I can't add anything, and I can't subtract anything. I can only multiply, or I suppose raise to an exponent. That would work because it would still be a polynomial, but I didn't think about doing that. So let's see. If I'm thinking about f sub 1, it's got zeros where I want it, but it might not pass through 1, 2. Let me draw a picture of what it might look like. All right, here we go. It might look like this. Let's see, tick marks 1, 2, 3, 4. It's going to have zeros at 4, 3, 2, but who knows what it does at 1, right? Who knows what it does? Well, half constructed so far, we can actually figure out what it does at 1. We can figure out the y value right there. We can figure out this y value. So if I divide this polynomial by its y value at 1, then this y value is going to get shifted down to 1, which is a lot easier to handle. So let's just evaluate this polynomial at 1. We're going to have to divide it by, oh my goodness, I selected blue, didn't I? All right, here we go. So we're going to have to divide it by 1 minus 2, which is negative 1, and we're also going to have to divide it by 1 minus 3, which is negative 2, and divide it by 1 minus 4, so 1 minus 4 is negative 3. Okay, so now when I input 1 into this polynomial, we're not finished constructing it still, but at the moment when I input 1 into this polynomial, it has it outputs 1. But I don't want it to output 1. What do I want it to output? I want it to output 2. So all I have to do now is multiply by 2. Now I'm done. I've created a polynomial that when I input a 2 or a 3 or 4, it'll output 0. But when I input the number 1, it spits out 2. That wasn't too bad. That wasn't too bad. Let's create the next polynomial, f sub 2 of x. And I'm going to do that in a different color. Let's see, green will work fine. So f sub 2 of x, well, I want it to have zeros at x equals 1 this time. Not at x equals 2, because I want it to pass through the point 2, 3, so it can't have a 0 there. But I do want it to have a 0 at 3 and at x equals 4. So that's beginning to construct that polynomial. Now what we're going to do is we're going to evaluate what we've got so far at 2, x equals 2, and we're going to divide by that number. So 2 minus 1 is 1. 2 minus 3 is negative 1. And 2 minus 4 is negative 2. All right, there's only one more thing to do here. Let's see. Now when I input 2 to this function, this polynomial, it's going to output a 1. So I need to multiply this guy by 3. So far, so good. Let me write down what we have so far. I've got f sub 1 of 1 is equal to 2, which is what I want. But f sub 1 of any of these guys, 2 or 3 or 4, is equal to 0, which is what I want. Now f sub 2 of 2 is equal to 3, which is what I was going for. But f sub 2 of 1 or 3 or 4 is 0, which is what I'm going for. All right. In a similar fashion, we can create easily the rest of the polynomials, which I will do in a hot second right here. Let's see. Draw colors, whatever. Let's just go back to black. F sub 3 of x, piece of cake. All right, x minus 1, x minus 2, x minus 4, and then we've got to put it over 3 minus 1, and then 3 minus 2, and then 3 minus 4, piece of cake. All right, and f sub 4 of x is going to be equal to x minus 1 times x minus 2 times x minus 3, all over 4 minus 1 times 4 minus 2 times 4 minus 3. Piece of cake. Oh, yes, and I forgot something, didn't I? I forgot something. I forgot my multiplication. I need to multiply here by the third prime. So the third prime is 5. I didn't need to scroll up to see it, but there you go. And this guy's going to be the fourth prime, so 7. And in fact, I could keep going. What's stopping me from keeping going? I mean, I would have to alter these guys a bit, so I won't keep going. But I've just created 4 polynomials. I've created 4 polynomials that have zeros at all integers, all the integers that I care about, 1, 2, 3, and 4, have zeros at all of those points except for this one passes through 2. This one, when evaluated at 2, passes through 3. This one, when evaluated at 3, passes through 5. And this one, when evaluated at 4, passes through 7. All right, so I'm nearly done. It's not going to look like a nice polynomial that has, coefficients and x raised to the n powers. It's going to look like this. The sum of f sub I of x from I equals 1 to 4, where f sub I of x is one of those guys, right? I could write out a formula for it, but I won't. But I will in a few minutes. That's not too hard. So I just created this polynomial. It's just the sum of these 4. So let me write an addition sign here, an addition sign there. Here's my polynomial. I'm done. But that only passes through 4 primes, right? Okay, there you go. That's my submission. I made it pass through 4. 4 is pretty pitiful. You think I could have done it with 5? Well, sure, if I was going to have done it with 5, I would have to add another polynomial, right? F sub 5, that's not a 5, f sub 5 of x. And that's going to be equal to, well, it's got to have zeros at 1, 2, 3, and that's a 3, I promise, and 4. And then you're going to have to divide it by 5 minus 1, that's 4, 5 minus 2, 5 minus 3, and 5 minus 4. And then you multiply it by the 5th prime, which is 11. Now, I'm not done. I mean, I can't just add this guy, because f sub 1, f sub 2, f sub 3, and f sub 4 at their current construction don't have zeros at x equals 5. So I would have to actually alter these guys. I would have to put an additional term on the top of x minus 5, and I would also have to evaluate f sub 1 at x minus 5 and divide that value. So 1 minus 5 is negative 4. So my basis functions change a whole lot, actually. X minus 5, I have to actually change every single term here. Let's see, 2 minus 5, negative 3, piece of cake. Then I've got x minus 5 here, and I've got 3 minus 5, negative 2, and I've got x minus 5 here, and down here I've got 4 minus 5, which is negative 1. All right, now that I've altered all the other polynomials, f sub 1 through f sub 4, and I have the correct f sub 5, now that's done. Now there's nothing stopping me from keeping on going. It's just going to look pretty, freaking terrible. So I'm going to try to write this in a way that will be arbitrary for any arbitrary number of primes. And I'm going to see if I can figure out how to pause this recording. And if not, I'll just upload a different one. Am I even recording? Let's see. Okay,